All right, so today we're going to start learning about vectors, the basics, but first I wanted to revisit a projectile motion problem from the parametrics unit because we only did a couple yesterday. And this is important not only for the quiz, but for the final. The projectile motion formula that, okay, don't have a cursor here, that is on the reference sheet looks like this, I think. Somebody check me out here. Whoops. Yes, because x goes with cosine and y goes with sine. Does that make sense to anybody? And this could be replaced with a negative 4.9 t squared if it's meters. This one is feet per second, so we're going to go with this formula. Okay. Jerome hits a tennis ball at an initial velocity of 38 feet per second. Where's this going? Okay. Be really careful because, oh, v sub 0, not at the top there. Sorry. A lot of times people like switch the v and the theta somehow. So this is an angle of 42 degrees, so that's the theta. Initial height of 1.5 feet goes in h sub 0. All right, so calculator on. And this one had, what were the numbers again? Thank you. And make sure you close that parenthesis, and then minus 16t squared plus, was it 1.5? Okay. Let's think about a window. What does t represent? Time in seconds. So tennis ball, time in seconds. I'm thinking 5 is plenty. 0 to 5 by 0.1. We're going to use t step 0.1. All right, how far away do you think a tennis ball goes? I don't know that we need 100 feet. Do we need 100 feet? 50? We'll check it out. We might need more. Height, I definitely don't think we need very much, right? I like to put a little negative so that it isn't cut off on the bottom. So I'm going to go like negative 5 to 15. Probably 15 is way too much. All right, I'm going to try it. Ooh, that is a excellent window. How are we doing? Anybody need me to put anything back up there? All right, so the question asked, could be anything, but this one asked, what is the approximate height of the ball? Oh, well, wait a minute. First of all, the question was, how far away will the ball land if it is not hit by his opponent? So what are we going to do there? Yeah, all we can do is trace. There's not a lot of helpful features in this, but this is the actual path of the ball. So we want to get as close over here as we can. Here it's 1.2 what? What does this number represent? Yes, this is y, so it's off the ground still at 1.6 seconds. Here it's underground, okay, it's already hit by negative 1.5 at 1.7 seconds. But if you notice, yeah, not too much difference there. I would probably take either one of those answers. Does anybody figure out how we could get a little closer to 0 here? We just need to add a tiny bit of time. So we could do like 1.63 or something. Okay, 1.65 if we wanted to be picky. You don't have to be that picky there. That's pretty darn close to 0, right? So the ball goes about 46.5 or 46.6 feet away. But if you put the 45 or the 48, I would have taken it because you can't be super exact in this format. So this question here, about how far away will it land, was it 46.6 or 48.6? Okay. What is the approximate height of the ball at the net if he's standing 20 feet from the net when he hits the ball? So here's the path of the ball. How do we figure out 20 feet away? Which one do we want to be 20 feet away? The X. So we want to go until X is as close to 20 as we can get. That's looking pretty good right there. Okay. If you wanted to try, 0.72 or something, you could, but it doesn't matter. All right, so 20 feet away, how high is the ball?
11.
Yeah, between 11 and 12 feet, does that... What I like about these kind of questions is you can determine, if it was a doubles and there's a player standing 6 feet past the net, so at 26 feet, would it hit him or not? Well, it's 11 feet in the air, so I don't think it's going to hit the player, okay? There's things you can determine as its real path here. Any questions? Feel like you're refreshed on projectile motion? Okay. Going back to talking about vectors, today we are definitely going to talk about sketching a vector. We're also going to talk about determining if something is a vector or scalar quantity. We're going to talk about breaking a vector into the horizontal and vertical components, and we'll see if we get to adding them. Okay? So the difference between a vector and a scalar. Well, a vector is a quantity that has both magnitude and direction. Okay? A scalar is a single real number. For example, here, a successful field goal attempt in football depends on several factors. Well, the speed of the ball after it is kicked is certainly important. The direction the ball takes is as well. So we need a vector because you need to say two things, what direction and what speed. So a scalar is something that indicates magnitude or size of a quantity, but it doesn't include direction. So here's some practice on this. A boat traveling 15 miles an hour, is that a vector? Does it have magnitude and direction? No direction, okay? Hiker walking 25 paces due west. Magnitude could be 25 paces. It's a unit of measure. We don't care. And direction is due west, okay? A person's weight on a bathroom scale. I would have said no, probably. I would have said that it's just a scalar. But anytime you weigh something, you're weighing the direction against gravity. So weight is a vector quantity as it is calculated pulling down due to gravity. Okay? I'm not going to ask you that on quiz, so don't freak out. 3 more real quick. A car traveling 60 miles an hour, 15 degrees east of south. Vector or scalar? Vector, okay. Parachutist falling straight down at 12.5 miles an hour. Why is it a vector? Straight down, okay. Child pulling a sled with a force of 40 newtons. It is a scalar because they don't tell us direction. If they even just said straight forward or something, we'd be good. All right, a vector can be drawn using a directed line segment, it's called. It looks like a ray from geometry, but it's not. Okay, the directed line segment with an initial point A here's called the tail where it starts, and the terminal point B where it ends. We will often draw them with a line segment at the end here, just a little showing that it's ending, not continuing on. It's not a ray. They will write that with this weird notation with only one arrow. Okay. Any questions about that? If a vector has an initial point at the origin, then it's called standard position. The direction of the vector is the directed angle between the vector and the horizontal line used to represent the x-axis. So the direction is going to be just like we were doing in trig. It's going to be rotating around this way, off the positive x-axis. The length of the line segment represents the magnitude. Remember, it ends out here at the end of the arrow, okay? And the book is really big on, like, we would decide if I'm supposed to draw 13 feet per second and I wanted to use a scale of 1 centimeter is 5 feet per second, I would have to draw this exactly 2.6 centimeters long. I'm not going to have us get out the rulers and do these to scale. We're just going to sketch them, okay? So one more time, a scalar has magnitude only. A vector has both magnitude and direction. And it is a directed line segment. The direction is indicated off of the positive x-axis. We are eventually going to talk about, these are on the top of 1B when we get there, but the difference between a quadrant bearing and a true bearing. How many of you had trig and remember bearing problems and you were a little frightened? Did you do some bearing problems? Probably not very many anymore, but a quadrant bearing is in our book always off, it's either east or west of the north-south line. So it's always off the north-south line, which is kind of easy to remember because the other kind we're going to talk about, true bearings, are always off of due north. So they will write something like this. This means off of south, go 35 towards the east. Okay? When they want us to use a quadrant bearing. A true bearing is a directional measurement off of north, and it goes clockwise, which kind of messes with us because everything else we've done is going counterclockwise. A true bearing is used, for example, in aeronautical stuff like, what's the guy who tells your plane it's time to take off? Air traffic controller. I'm like drawing a total blank. Air traffic controller, they use these kind of, and it's off of due north, okay? And it's given with 3 digits. So if it happened to be only 25 degrees, they would write 025. But for this particular vector, if we were measuring it at a true vector, it was 35 degrees towards the east off of south, or it's 45 degrees off of due north. Little geometry in there. We're subtracting from 180, right, to find the other part. Was that someone? Not me? I hope mine's off. All right, use a ruler and protractor. We don't have to use a ruler and protractor, but we will have to indicate this. It says 20 feet per second, so you would just draw a line and tell me it's 20 feet per second. Okay, that's all I'm going to ask you to do. But then it said at a bearing of 030, so you would need to know that that meant off of due north, and you would draw it and label it in here. Seem okay? So here's 30 miles an hour. I would ask you to just label this 30 miles per hour at a bearing of, and this kind, remember, always starts off of the south, and then it says 60 degrees towards the west, so you would put that arrow and that indicator of direction in there. So let's try these. Number 1 says 60 pounds of force at 125 to the horizontal. Whenever it says to the horizontal, it's just indicating off the positive x-axis. So we need to indicate that we are going around 125 degrees. Can you try to make that sort of accurate, Lillian? Not appropriate. 125 degrees would be, less than halfway in here. 60 pounds of force, so we're going to just label this. Put a little arrow to show that it's stopping, it's not going on forever, and label this 125 degrees. Any questions? Yes. We don't ever go clockwise unless it's off of due north. Let me see if there's an example. Is it because of the to and from that you guys do it in physics different, or what are you saying? Go ahead, Keaton. Neither of these said from the horizontal, did they? Okay, I'm going to pause this. Okay, just for clarification, this is correct that the book goes off the positive x-axis, and anytime it measures with the horizontal, it's going in this direction. Okay, the only thing that goes the other direction is when we do off true north. All right, we're going to come back to this question in a little bit and talk about the components. Number 2 says 55 miles an hour to bearing of. Where are we measuring off this time? What does this? Yes. And 45 doesn't really matter, right? Because it's going to be right smack in the middle. But you always start off of the north-south line. So this one is starting off of south, 45 degrees. Which way am I going, left or right here? Right. Towards the east. Okay. All right. And I'm supposed to label this vector as 55 miles per hour. We good? Number 3 is this quadrant bearing again. And it says off of north, going 40 degrees towards the west. So the 40 degrees is in here. And this is going to be 30 meters. Sorry, that's written poorly. And one more. 150 yards at 20 degrees to the horizontal again, just here, 20 degrees. And 150 yards out to here. Can draw these? No big concern? It does say labels on the diagram. No, not okay. Find your packet. All right, we're not going to do a whole lot with this, but the idea of parallel, if we were going to use tip to tail or tail to tail addition later, you would need to understand equivalent parallel opposite vectors because we'd be moving vectors around, but we're not going to do a lot of this. A and C are called equivalent because they're the same length and the same direction, okay? A and D would be the same length, but they're not the same direction. C and E would be opposite vectors because they're exactly the same length and going in exactly opposite directions, or parallel vectors. Okay, A and C are also parallel, but yeah, good enough. We're not going to talk much about that. But we do need to be able to find components, okay? 2 or more vectors with a sum that is vector R are called the components of R. So while components can have any direction, it is often useful to express or resolve a vector into the components that are known as the horizontal and vertical components. Okay, so we're going to take any force and break it down into X and Y horizontal and vertical components. And then we're going to use those to add. So this is pulling a wagon, but we can still break it down into separate horizontal and vertical components. So Heather's pushing the handle of a lawnmower with 450 newtons of force at an angle of 56 degrees with the ground. So if we wanted to find x, what trig function would help us find x right here? From this angle, this would be cosine, right? We would have the cosine of 56 equals x over 450, or 450 cosine of 56 would be the horizontal component. Everybody good? What about the vertical component here? Which function is across? We'd have the sine of 56 equals y over 450, or y equals 450 times the sine of 56. So when we type those in, you get the horizontal and the vertical components. And it can be written, we're going to practice this more tomorrow, but as a across or x number and an up and down y number. So we are going to do that with this question. Jamal pulls the ends of a rope tied to a dinghy with a force of 50 newtons at an angle of 60 degrees with the horizon. Draw a diagram. We did. And now resolve it into x and y components, or find the magnitudes of the horizontal and vertical components. So to find x, we would have adjacent to the 60 degrees, which would be cosine. And the hypotenuse is 50 newtons. So to find x, we'd have 50 times the cosine of 60 degrees. I'm leaving it like this for a second because we're going to see a pattern here. And the up and down, or y, is across from the angle. So we have the sine of 60 equals x over 50, or 50 times the sine of 60 will give us y, not x. My bad. I should be more careful about what we're talking about. So we can type these in and get numbers, okay? Anybody know in their head which of those values is 1/2 and which is square root of 3 over 2? If you're at 60 degrees, you're up here, so you went over a little bit and up a lot, right? So it would be 1/2 here, which would make that 125. And the y would be square root of 3 over 2. So this would be 50 square roots of 3 over 2, or 25 square roots of 3. And I'm good with a decimal. I'm just trying to bring back some of your trig knowledge about the unit circle. What did they have? You have this done on your sheets? They just had the decimals, right? 25 and 48.3. Okay. Component form. If, this is important, if we use an angle with the positive x-axis, this is the only time this works, but I'm going to always use it because it's going to make life easier. Then to find the component form, do you notice what we did here? We ended up with 50 times the cosine for x and 50 times the sine for y. Does that make sense to everybody, that x is cosine and y is sine, if you know your x or y over r? Okay. We're supposed to go back and do 1 through 4. Now we could spend a lot of time being real careful how we draw this, okay? Or we can do what we just did and talk about the angle off of the positive x-axis and breaking them into components using that definition. X equals the radius or the length of the vector times the cosine of the angle, and y equals 60 times the sine of the angle. Now, we're going to get a negative number because we use this 125, but should we have a negative x? It's pulling left, right? If we're talking about the components, we're going to want this as a negative and a positive. So make sure your calculator is in what mode? What are the 125 in? It's 125 degrees, so we need to be in degree mode, okay? The function, we're not graphing, so it doesn't matter what if you leave it in parametric. But this question was 60 cosine of 125 and 60 sine of 125. So it's pulling to the left 34.4 and up 49.1. I already forgot what I just said. Like that? Okay. Now, we're not really concerned a lot about direction yet today, but that's how we're going to do these. So I want to stick with the method we're going to use all along. Number 2. Okay, what was the big deal? You can only use this when you are using the angle off the positive x-axis. No matter what they gave you, you need this angle. Is it going to be different on this picture? Still 45, right? Actually, we should call that what? Negative 45, because we're moving down. So we're going to use 55 cosine of negative 45 degrees and 55 sine of negative 45 degrees to find those components. If you only want the length, you could use positive 45, but that won't indicate the direction, as in that it's going down. So the cosine should be positive. I don't know what decimal we get. Anybody? 0.5. Okay. And that should be for both, right? 38.9 for this one as well. But the y component is going down, so I'm going to put a negative. And it should have turned out negative when you typed it in here. All right. So again, let me go back to this slide. You have this on your notes, I'm pretty sure at some point. But it says where theta is the angle with the positive x-axis, okay? The only time this works, our cosine theta and our sine theta, is if you have it with a positive x-axis. So can you try 3 and 4? Maybe tell me what angle you're going to use for this one. Yep, 40 plus 90, you're going to use 130 degrees. And this one's just 20. So it is the magnitude, which was the 30, times the cosine of the angle off the positive x-axis. So you had to use some geometry. You had to do 90 plus 40 to get that angle. So the first one should be negative positive, right? And the second one will just be a positive positive. Chadwick, can you tell me what you got for number 3?
Yeah.
Kayvon, can you tell me what you got for 4? Did you get it typed in yet? Okay, about 141. Good enough. Okay. Any questions on those? Breaking a vector into components. Very important. All right. So you have this on the back, but we have already talked about this. So for our book, be very careful. Bearings are either going to be off of north or south. So they're going to start with where you start, north, and go 20 degrees, 22 towards the west. That one would look like this, with a 22 in here. Or off of north, clockwise, like if they don't tell you a direction and it's a bearing, it always goes off of north in a clockwise direction. So 220 would be down here if you were doing a bearing question. All right. So draw a diagram that shows the resolution of each vector into rectangular components, then find the magnitudes of those components. They just want to do exactly what we just did. So 7 inches at a bearing of 120 from the horizontal is going to be measured around this way, 120. And it's going to be 7 inches is the magnitude or length of the vector. Now what? That's it. Anything going to have a sign on it? But can you predict ahead of time? It's in this quadrant, so it went left and up. So it should have what? Yes, should be negative and then a positive. Let's see, that leaves 60. So the y, yeah, this one should be 1/2. I was just trying to figure out which one had a 1/2, and this would be 7 square roots of 3/2. But what's that give me? 6.1 is fine, yeah. So it's negative and positive. Now, it says find the magnitudes of those. So if I were to draw it broken down into 2, this length would be 3.5 inches, and this length would be 6.1 inches. Okay, it doesn't say that indicate the direction, but if you just write it this way, it's fine with me, and then we'll use it that way for another question. All right, so where is this one measuring off of to start with? Off of north. Yes, off of north, 50 degrees would be a little more than halfway towards west. And it's 2.5 centimeters. So if I want to use component form, what do I have to do? Yes, because I have to have the angle off the positive x-axis. So 90 plus 50 is, so I'm going to type 2.5 cosine of 140 and 2.5 sine of 140. And it should come out again negative positive because of the quadrant we wound up in. Anybody type in for me? You're fine. 2.5 cosine 140 and 2.5 sine of 140. Did I do sine first? No, I didn't. Negative 1.9 and 0.43, something like that. Did I type something wrong? Entirely possible. Yeah, I put 170. Don't listen to me. 1.6 is beautiful. It should be close to each other because it's almost a 45, so the numbers should be close. All right. What's different about this one? True bearing of 140. Does anybody remember what that meant? Off of north. Which way though? So 140. Where's the angle with the x-axis? How much is it? You could go all the way around this way off of, but yes, we could call this what? Negative 50 because this is 90. Okay, so it's a 50-degree angle in here, but if we want direction, we need a negative. So we're going to have 4 centimeters here. Yes. Yes. If you did 310, is that what it would be? Positive 310? No, they have to add up to 360, right?
Oh.
So it would be 270 plus this 40 degrees in here would be 310. The north, yeah. 310 would work. All right. So 4 cosine of negative 50 and 4 sine of negative 50. We should get a positive and a negative this time. Nice. All right, one more here. It says Nadia's pulling a tarp along level ground with a force of 25 pounds. If the tarp makes a 50-degree angle with the ground, so I'm just going to assume she's going this way. It doesn't matter because they really only want the components, not necessarily the sign on them, but 25 pounds of force. What are the horizontal and vertical components? So as long as we've drawn it this way, we can just use what? Yep. $15.1. Okay, thank you. And 19.2. If I wanted to check those, could I do Pythagorean theorem on those numbers and it should get back to 25, guys? Do you see what I'm talking about? We got a little right triangle down there. Okay. By the way, this is horizontal and vertical, if it were to ask that, right? All right, I am going to attempt to start a question about, we're going to revisit this tomorrow about the different ways you can add. I'm just going to kind of fly through this just so you've seen it, and then we'll do it next Tuesday when you won't remember anything, right?
Right.
Okay. But I'm just going to show you bits of this real fast. It says the airplane is flying with an airspeed of 310 knots from a heading of 050. That's here. So what's this angle, guys, if this is 50? Okay. And it was 310 cosine of 50, 40, kidding. And 310 sine of 40. All right, and then it says the wind is blowing from a true heading of 125. So it's 125 down this way, but it's actually blowing from there. So it's pushing the plane over here. If this was 125, we do 125 minus 90 and we get 35. We do vertical angles. This is 35. 180 minus 35 is actually 145. Did I do that right? So the wind actually has 78 cosine of 145 and 78 sine of 145. And then what we're going to do is add those together and get components here. And then we're going to have to find the magnitude using Pythagorean theorem. Okay, so this is way easier than what some of you do in physics when you do tip to tail and you have to use law of sines and cosines, because those really require that you're graphing things accurately. All right, so the homework is basically all on worksheet 1.5, okay? Worksheet 1.5. It's circled which problems you have to do. There's not very many of them, and I'm not sure you'll be able to finish 24 and 25, so there's like 5 problems Any questions? All right,